Hello, everyone. As usual, I'm here to talk about your lab assignment in SPSS. So, we're going to be going over the fifth lab assignment. Some good news is that this is the last required lab assignment. I'm sure people will be happy about that, and I totally understand. There's plenty of other stuff to work on. But the next two assignments, so 6 and 7, I believe are just for extra credit. So I will still, post information related to those, but I just wanted to give that tidbit of good news in case you haven't already noticed in the syllabus. And in my personal opinion, it's pretty straightforward. It's a little bit different than, and maybe some of you guys will think it's quicker than some of our previous lab assignments. I think our previous assignments, gave us a lot of breadth or, variety on the different things you can do in SPSS, especially related to cleaning and organizing your data, which is usually more than half the battle. When you are dealing with data, usually the analysis part is very brief. It's a lot of cleaning or, computing variables. So the setup or the prep that goes into analysis tends to take much more time than the analysis itself. And that's also true because usually going into it, you know what analysis you're going to run. So you don't spend a lot of time at this point trying to figure out what analysis to run because usually you're, planning for this ahead of time. What I've always been taught and what I think is, the best practice is you plan out exactly what you're going to do ahead of time, because when you're setting up the study or say programming a survey or writing a study script, whatever it may be, whether it's like an in-person study, like a lab-based study or a online study, a survey, your analysis greatly depends on how you ask the questions, how you set up the variables. So obviously when we get to the data set, we have a very simple, this is my output, but we have a very simple setup here, which is almost never how it looks. Usually you have, maybe scale items. So maybe there's 10 items on a scale. So you'll have, if you're measuring stress, you'll have stress 1, stress 2, stress 3. Like you'll have different columns for all of those items that you then have to compute a like composite stress score or something like that. So your data set is almost never this clean to start with. You'll get your main ones like ID automatically, like there's nothing you have to do to ID, or gender if you coded your survey correctly, where there's already like numerical values coded as the different groups. Age, usually if you like let people use a sliding scale or a text entry. If you do a text entry, a big thing to know with like any sort of like numerical entry is to set it to only allow them to like allow participants to enter numerical values, or else you'll get a lot of like 24 years, or another one will have year. Like it'll always look different, and because SPSS is set to the numerical values already, we don't have to worry about that. But sometimes when you're pulling your survey data like directly from the source and you allowed people to just enter in whatever, you'll get very inconsistent values, if that makes sense, like inconsistency in how they're formatted, which makes analysis harder. So it's like I already have this data set up properly, so we're good to go. But I think a lot of our earlier lab assignments really covered that like groundwork that goes into setting up your data. So there's just some more context there. But for this assignment, we are conducting an independent samples t-test, and then you're going to make a chart to show your results. So you'll have your t-test output, the chart, and a brief little write-up on the results. So that's all broken down here. So we have conduct a t-test, which is majority of where the points are coming from, error bar chart, and results summary. So broken into 3 parts, but all pretty straightforward and don't require a lot of different steps in SPSS itself. So I feel like here we're getting a little bit more depth versus that breadth or variety in all the different things you can do in SPSS. So this is a little bit more into the weeds of what you would do for a statistical test and then what you have to do after that. So usually you need some sort of visual and then a write-up. So I'm going to take you through that. It's not going to take very long, but I will explain the data set provided. As always, you can, download it from the assignment details, and you're going to be working in that. And like I said, it's going to be pretty quick what you have to do in SPSS, which is nice. But just to explain the variables that we're looking at. So this data comes from an experiment testing whether anticipating a low or high stress situation influences how much people talk during a 10-minute interaction. So here we're dealing with an experimental manipulation and a behavioral outcome variable. So rather than asking someone how do you feel, they're literally being observed, and it's documented how much they talk during the 10-minute interaction. So each participant was randomly assigned to one of two experimental conditions, either the low stress condition or high stress condition. And what low or high stress refers to is just the context that participants were given for the study. So one condition was told that they were just completing a personality questionnaire, so very low pressure. They're not presenting it to anyone, they're just completing this questionnaire. The high stress condition, participants were told they would soon be interviewed by a panel of specialists. So people specializing in these questionnaires, so a little bit more high stakes, however you want to call it, but different than just completing a questionnaire on your own, which if we want to break this down further on why this would be considered the high stress condition, it's a huge thing we consider in research when we're conducting surveys. Is often we can ask more sensitive information in and I don't mean identifiable, something that compromises their privacy. I just mean literally more sensitive related content about someone, and get more, I don't want to say accurate, but more honest answers from someone when they're completing the questionnaire on their own versus being interviewed by someone, let alone several people, especially if you're asked about maybe behavior that is considered to be sensitive or private. You're just more likely to get more honest, representative answers from individuals when they're answering it on their own versus when they have to out loud verbally talk with someone who's asking them the questions and reacting in front of their face. So that's another way you can think about this low and high stress condition. And after receiving these instructions, and they were randomly assigned to either group and were given those instructions, each participant spoke with an experimenter for 10 minutes. And the variable talk in our data set represents the percentage of time each participant spent talking during that period. There are also some other variables in there, we have our normal ID variable, gender, age, things like that, but we're not doing any analyses with those, but they are in the data set. And so the goal of conducting this t-test is to determine whether participants in the two experimental conditions differed and how much they talked on average. So our first part is to conduct an independent samples t-test to determine whether the amount of talking differs by stress condition. So you have your instructions here. I'm going to show you exactly where to go. So you go to, so here's our data set, as I mentioned. So really the variables we're working with today are stress and talk. So just so you know, these other variables are in here, but we don't need them for our purposes today. So stress, again, I already have this organized, labeled. So if we go to our stress variable, we see that 1 signifies the low stress condition, while 2 signifies the participant being in the high stress condition. And talk is, as we mentioned, the percentage of time that the participant spent talking across the 10 minutes. And if you want to get into how we got this variable, basically sessions would have been recorded, and then researchers, research assistants would go watch them, and then time, literally any time the participant was talking, start a timer, end a timer if they stop talking, that sort of thing. So we literally got a, exact calculation of how much time that participant spent talking in that 10-minute duration, and this variable represents like percentage of that 10 minutes, so not actual time. So that's another thing. So when I got this raw data set, I had to compute a variable to take the maybe raw amount of time spent talking to a percentage over 10 minutes, if that makes sense. So those are the two variables we're working with. And all we need to do is go to Analyze, Compare Means, and here we see some different options. So I'm just going to talk about our t-test today. So don't worry about summary independent samples t-test. I'm going to go over the other main kinds that you come across. So one sample t-test, independent samples t-test, paired samples t-test. Those are the ones that are going to come up, and you have to decide which one applies to your situation usually. As the assignment indicates, we already know that we need an independent samples t-test, but I want to talk about why these others don't work or what situations they would be used in. So a one sample t-test, the best example I can give for this is usually like in manufacturing, is like the idea that comes to mind, or you could think of it in like medicine or something like that. But a one sample t-test is what it sounds like, in that you only have one group or one sample that you're working with. So you don't have two different groups that you're using. What you're doing is you've conducted a study with one sample, and you're comparing that sample to the population. And the biggest thing that when I was learning about this is I was trying to think of instances where you would with absolute certainty know the population mean that you're trying to compare it to the sample. And like I said, the example that comes to mind is manufacturing. So typically in manufacturing, so say, in packaging a bag of like a snack size bag of chips, say that there is a certain weight that bag of chips is supposed to be, that maybe the company claims, in every bag you get, however many grams. I don't even know how many grams a bag of chips would be, but say 500 grams. So if every bag of chip, if the company's manufacturing standard is every bag of chip is 500 grams, that is a case where you can then conduct a study getting the actual bags of chips, so you're getting a sample of chips, and comparing it to the population mean, because what it's supposed to be is 500 grams. So then say you would take a sample of like 10 bags of chips, and you're trying to figure out, okay, how many of these are actually 500 grams, or like, is my sample mean, like weight of these bag of chips, so out of 10 bags of chips, my mean is it statistically different from 500, because it's supposed to be 500. So that's an example of when you would use a one sample t-test. Like I said, the same could be said for in medicine, like with specific like drug dosages that you're working with or anything like that. Independent samples t-test is what we're working with today. I'll come back to that. A paired samples t-test is, again, the name hints at what it means, but without more context, it can sometimes be like, well, how is that different from comparing two means? Like, we have two groups. We have a low stress condition, a high stress condition. Is that not paired samples? There's two, there's a pair. So the context here is that why it's not a paired samples t-test is because the same people or participants are not undergoing the same conditions. So paired sample t-test is basically what we think of a within person design or a within whatever. It doesn't have to be a person. So again, it's not always people that are, being studied. Again, in the manufacturing sense, maybe it's bags of chips, or you could think of it as like cars or plants, anything you could study that you could, you could have a subject, what you could say, whatever that subject is, undergo both treatment conditions or both groups that you're interested in comparing. So, for example, I'm trying to think of cars. I've heard an example for paired sample t-test about cars. Like, say, there are two different brands of oil or fuel, whatever you want to think of it as, two different types of fuel that you're using. So say you're comparing like unleaded with the premium, and you're trying to get an understanding of, does it actually make a difference? Well, one way you could do it is randomly assign different cars to those different fuel options. But that also, there's a lot of considerations with any sort of experimental design that you're doing. But one thing someone could say is like, well, there's so many different types of cars, and like, so what if those cars have been, have more mileage than other cars, or like, is that a fair comparison? And the answer is that when you're using random assignment, it kind of takes away those issues. So random assignment always gets rid of those issues. But, for some reason, maybe you're interested in the same car undergoing both different like treatment options, treatment groups that you're testing to see if the performance differs. That brings its own issues, because then you have issues of like, with people especially undergoing different treatment conditions, like too close together. There's like practice effects. So are they just getting better at what you're assigning them? Or, with cars, is it, are you truly getting a test of better performance over time because of the fuel, or are there other factors at play? So, there's always things to consider. It's never perfect, but as long as you're aware of those considerations and you have some rationale for why you're picking the specific test that you are, maybe a lot of between group or independent samples t-tests have already been conducted, and so you want within subjects design or paired samples t-tests where the same subject or car or person, whatever the situation is undergoing both treatment options. So paired sample t-test just means that you're dealing with basically 2 time points, or each subject, again, whatever you're dealing with, is undergoing both treatment options that you're testing. So you're getting 2 different means. Okay, so this is the, mean miles per gallon for cars who get regular unleaded, and this is the mean miles per gallon that you're getting for premium. So you're still getting 2 different means that you're comparing, but the basically with paired samples t-test there is an assumption that, they're not necessarily, those means for the same car are not independent of each other. They are like paired or connected to one another because it is the same subject undergoing those treatment conditions, whereas independent samples t-test is now exactly what it sounds like. Independent samples. They are independent of one another, so what one group is assigned to is independent of a different group. It's not tied to it being the same individual undergoing both treatment groups. So hopefully that makes sense. But again, independent samples t-test is what we're going with, so you just select that. And just as a refresher, because I was talking about that for a while, you go to Analyze, Compare Means, Independent Samples t-test. And what we want to do is move stress under our grouping variable and percent of time spent talking, or talk variable, however it displays on your end. Again, this is just using the full variable label. So you can also change this by right-clicking, and here it says display variable labels. You can switch that to names, and vice versa. And then when you get here, so we put stress in our grouping variable, but you also have to define the groups. So you just basically, this is very it seems maybe unnecessary because it seems very intuitive because we labeled our groups as 1 and 2, but you could have them labeled differently. So just because these line up doesn't mean they will always line up. So it's just saying group 1 is 1, group 2 is 2. But you could have different labels here, like 0 and 1. So this could be 0, 1. So group 1 is actually our 0 value. Group 2 is our 1 value. So something to keep in mind. So again, we've moved talk to our test variable, stress to our grouping variable, and we've defined our groups. Need to do. So I'm going to hit OK. And I'm not going to show my output because a lot of our assignment is based on you interpreting the results. So if I show the output and I talk about how to interpret the results, again, everyone's assignment could look exactly the same. When I'm really more interested in how you guys interpret it rather than how I interpret it. I know how to interpret the results. We need to get you guys to interpret the results. So apologies if that is, textbook annoying instructor, teaching assistant nonsense, but it is for you to learn. So, all right. So part 2 of our assignment is creating a graph showing the mean talking percentages by group. So what you want to do is use an error bar chart specifically, and then you're going to have talk as your variable and stress on the category axis because that's our categorical variable, if that makes sense. Hopefully it does. So how do we do this? So one way to do it that I'll show you now is graphs, legacy dialogues, and error bar. And as usual, you want to keep summaries for groups of cases checked. Again, this just means we have a grouping variable that we're interested in breaking up those results by. So as I mentioned, the talk variable, or percent of time spent talking, goes into variable, and then stress goes into our category axis. And then if you go into, so something extra that I don't think we've done before because we've done our bar chart but not an error bar chart, is we want our bars to represent our standard deviation and make sure 2 is your multiplier. So essentially that just means 2 standard deviations within the mean is what our bars represent. Okay, so moving on to the last part of your assignment, the results summary. All in all, it should be at least 3 sentences long, if not 4. So 3 to 4 sentences should be written out. In those 3 to 4 sentences, you're reporting the descriptive statistics, which refers to like the mean and standard deviations. So that's like the actual observed, like what's the mean of these 2 different groups, what's the standard deviation. And then you follow that up with your inferential statistics. So the actual statistical test you ran, independent samples t-test, you get statistics like your t statistic or your t-value, degrees of freedom, and p-value, which are all standard to report whenever you conduct a t-test. Another thing you want to report, which I'll go over a little bit more about like what this refers to or what this means, but you want to indicate whether your assumption of equal variances was met or violated based on the Levine's test. And this is just referring to the output from your independent samples t-test, but something else you get is the Levine's test, which is not actually testing or comparing the means against one another, because again, that's what you're getting here. That's like what the goal of the test is. But typically with every statistical test, there will be some, assumptions that also need to be tested, again, related to whether or not your data is normally distributed, usually, or in this case, has equal variances. And I'll explain again a little bit more about this later, but I'm just letting you know that this is another part of your output that comes from that independent samples t-test that you ran. So you don't have to do anything extra to get this output. It comes automatically. So again, you'll get these two tables, and I'll give you a little bit more insight about how to interpret or read the table. So you need a sentence on, the reporting the descriptives. Again, that's not just putting the numbers there. It's still in a complete sentence. So you have to kind of write it out while also including those statistical values. So I have an example down here of typically how that's structured without giving too much away, but there's going to be like a sentence reporting what test you ran, what variables you were examining, and then you're going to report, okay, did someone have a lower or higher mean? And then you just follow that up with the actual statistical values in parentheses. And then the actual test statistic or result of the t-test. So you'll report those as well. And then you can briefly touch on whether or not those the assumption of equal variances was met or violated or not based on the Levine's test. Again, that's just something that's usually standard. It's with any statistical test, sometimes there's different tests that are going along with those assumptions. So Levine's test is really common when you're comparing means across different groups. So when you have different experimental conditions, different distinct groups or assigned conditions, Levine's test is, you're going to see it with most of those. Whereas, other statistical tests may have other assumptions that need to be met or different statistics that are used to test that other than Levine's test. So you'll briefly touch on that. And then you just want to end with like kind of breakdown. So you reported the descriptives, you reported the result of the statistical test through the inferential statistics. But then you just kind of want to break down of like, okay, well, what does that mean in like real world terms? So if you could put this in simpler terms, essentially, rather than thinking about this like, well, when they're experimentally assigned to the low stress group, they do this. Try to break it down in real terms. So in these low versus high stress situations, what happens based on the results? Basically just trying to break those results down in very simple terms. Like what's the takeaway? Even if it can't necessarily be generalized, shouldn't be generalized, but what's your takeaway from the result of this test? Basically just a way to kind of ground the reader in, okay, I told you all of these important statistics, which are important when you're doing this research in order to be easily verified, validated. People know, oh, so they're reporting all of this, so I know that they did this correctly. Or, oh, they did a t-test, so as they should have, they looked at the Levine's test and assessed whether or not equal variances could be assumed. All of those things are important in reporting so that other like colleagues, researchers, academics can look to your work and verify that it was, up to snuff what we call peer review. And the best way for someone to be able to verify that is to report on it. Otherwise, if I'm reading something and I'm like, well, they didn't mention a Levine's test, so I don't know if they just did it and, the assumption was met, so they decided not to report on it, or if they don't know that they're supposed to look at this, and therefore now I don't know if their data was violating any normality assumptions. So all important things to report, but then you want, a closing sentence takeaway of like, okay, what do I take away from this specific result? How do I put this in simple terms? Okay, so that is the gist of your assignment. Before I end the video, I just want to talk a little bit more about the output that you get from the t-test in terms of what you're looking for, how to interpret it for your result summary. But what I want to do is not give away the answer directly. So, one second. Okay, this is so annoying, I'm sure, but I've fashioned a little way to hide my output while I try and explain how to look at this data. So as I mentioned before, the t-test gives us 2 tables, and one of those tables is going to be our descriptive statistics, or how it's referred to here as group statistics. So this is the first part of your result summary. So you just need the breakdown of, for these samples, I need the mean standard deviation. This is also obviously a way you can check, like, do I have balanced sample across for these 2 conditions? So how many are in the low stress group versus the high stress group? So that's all you need to know here. This is just literally telling you the mean amount, the mean percent of time spent talking across this condition. So of all the people in the low stress condition, what is the average percent of time they spent talking across that 10-minute period versus in the high stress condition, how much time on average did they spend talking during that 10-minute duration? So along with the standard deviation. So again, that's just important to understand our sample, and just visually you can get an idea of, are they different from one another? Is one higher or lower? But then that doesn't tell you anything about, are they statistically different from one another? So then we need the second table, which I'll show you here. All right, so now I've just scrolled down a bit so we can see what the second table looks like. So our independent samples test table. And in this table, you're both getting the information about the Levine's test on the left side and then the actual t-test on the right side. And the way that it's broken down is actually helpful, but it can be confusing because you have 2 different areas that say, p-value, you have an f-value, even though it's a t-test, so you want the t statistic. But there's a reason for that. So again, the Levine's test is run automatically when you do an independent samples t-test or other tests where you're comparing means across, like, between groups. And what this does is tell us if we have equal variances across our groups. And that doesn't mean that our groups are the same, but it is telling us the relative spread of our groups. So for our low stress condition and our high stress condition, are their spread or variances somewhat equal? And the reason this is important is, so imagine like one group had like ranges, like people who ranged from talking anywhere from like, say, 2% of the time, so maybe they barely said anything, to like almost the whole time, 100% of the time, or like 90 something percent. So say the one group, could be either one, has that variability of people who spent like very little amount of time talking or a very high amount of time talking. But then another group is like really concentrated where mostly everyone in that group spent like maybe 40% of them 40% of the time talking. And you could think of this as a result of the experimental manipulation. But a problem with this is that even when two groups are statistically different from one another, so on average they score differently or talk different amounts of times, you still want a fair spread in the data. Even when two groups are on average statistically different from one another, you're still going to have, or you still should have, people in there that represent, maybe they're a standard deviation away, 2 standard deviations away, or even up to 3 standard deviations away. Like, without being an outlier, you'll still have data farther away from the mean. So you don't want all of your data in one group to be concentrated really heavily around a certain part of the data. Meanwhile, another group is more evenly spread. Because something that would tell me is that we don't have a big enough sample, which is likely with this data. There's only 30 cases in this data, or IDs. So in that case, you don't necessarily want to take the result of that statistical test and run away with it and say, oh, look how different these groups are. If you didn't have equal variances across the entire sample, then that means likely that you have some sort of like sampling issue. Just a limited sample, didn't sample from enough like sources. Again, you're not getting a representative sample. So you don't want to necessarily take those results away and run away with the conclusion that, oh, because we had this experimental manipulation, that's why they scored so differently. Like, even when groups score differently from one another, there are, people in that group who don't score all that differently from another person, or they just have a lot of variance in their scores, high or low, whether or not it's due to the experimental manipulation or not. Hopefully that makes sense. But essentially because every person's different, you should not see a group where everyone is scoring like the exact same. So maybe if you take that person and put them in the other condition, maybe they would score significantly differently. So thinking about that paired sample t-test design. But in general, because everyone's so different, you should still have equal variances or an even spread among the entire data. You shouldn't, because that also violates our assumption of normality. If you have unequal variances, that means that your data is not normally distributed, because you don't even have people scoring 2 standard deviations away, 3 standard deviations. You need some people in the group to score away from the mean in order for it to be considered normally distributed. So yeah, equal variances doesn't mean that the groups are the same. It just means that there is, equal amount of spread or variability in the data, so that it doesn't completely throw off like normal distribution in that group. So again, you want equal variances, but there's a way to tell whether or not you do, and the independent samples t-test table gives you the result either way. So that's why there's this like little break here. So basically there will be a row of numbers that you can interpret if equal variances are assumed. So if that assumption is met, then you go with the top row. If there is a violation, which I'm going to tell you how you know if there's a violation, like glaringly, by using this test. But then you can just go with this second row and you say, the assumption of equal variances was not met, it was violated, evident by the Levine's test, and then you would then report the p-value of the Levine's test, which is right here. So the Levine's test, which is again on this left side, and you can kind of see it's like separate from what's down here, which is your entire t-test, has its own p-value. And when you're discussing whether or not, this assumption was met or violated, you report this p-value. But it works on reverse the way you interpret p-values for statistical tests usually. So I know that's probably really confusing, but it's just one of those things that you learn and you have to commit to memory, or just keep looking up every time you're doing SPSS. But essentially, if the p-value for the Levine's test, so this p-value, the one that just says SIG, S-I-G, period, if this p-value, so SIG, by the way, stands for, that's just your significance value or your p-value. If this is above 0.05, that means equal variances can be assumed. If it is below 0.05, then equal variances are not assumed. So that's the important takeaway there, is that there are two p-values in this independent samples test table. The first p-value or sig value, significance value that you get, is right under the Levine's test. Another way to think about this separate is, again, because it has an F value or an F statistic, that's not your T statistic. So it's a different statistical test that's happening here. For the Levine's test, it's an F statistic, but you really just need this p-value. And again, if it's above, exceeds 0.05, then equal variances can be assumed. Means, your data is meeting the assumption of equal variances. So there is, an equal spread across the groups. Yeah, and this variances is referring to the different groups that you have in your data, not broadly. So equal variances across those groups that you're testing. So if this sig value is above 0.05, equal variances can be assumed. If it's below 0.05, you can still use the output. You just need to go in the second row. So again, there will be numbers in both rows, both equal variances and equal variances assumed and equal variances not assumed. There will be output in both rows. Based on this p-value here, you choose which row to interpret or report. So if the p-value for the Levine's test is above 0.05, you can go with the top row. If it's below 0.05, you would go with the bottom row. So then you get to the actual t-test, and again, this is going to fall in line more with what you're used to, but you want to report the t-value, again, from the correct row, the correct degrees of freedom, and then this is the p-value that you're paying attention to determine whether or not your groups are significantly different from one another. So again, the t-test is what's testing, are these means equal to one another? So for the Levine's test, you want equal variances. For the comparison of means, what you're typically looking for, not saying you are wanting one result or another, like one result is good and one result is bad. So if you have insignificant results, it's not a good or bad thing, it's just the result. But typically what you're looking for it to be significant, that's typically what people are asking, not necessarily what's good or bad. But in order for the t-test to be significant, this p-value or sig value, significance value, and you know the difference between these because this one is one under the t-test, like header right here, whereas this one is under Levine's, but it also has the two-tailed in parentheses after. So the sig dot two-tailed value is the one you want. So this is just the p-value for your t-test. So if this one, probably as you're used to hearing, but if it's below 0.05, that means that the two groups, the means of the two groups are statistically different from one another. That means one is scoring higher or lower than the other from a statistical standpoint. So they're statistically different from one another. So once you interpret the Levine's test, you can then report the statistical test, the t-test results. Decide it after you decide which row to go with based on the Levine's test. And then you can interpret and say, once and for all, in this study, where were the groups, experimental groups, significantly different from one another? And if they are, which one was higher or lower? What does this mean? If they're not different, what do you take away from that? What is the interpretation there? So whatever it may be. All right, I've now talked about everything you need to do this assignment without giving any necessarily answers away, but telling you how to interpret. So again, part 1, conduct the t-test. Your output, the tables I just showed, should be in your output file, both the group statistics and the independent samples t-test tables. And again, there's nothing special you have to do to get those tables when you're running the t-test. Like, you don't have to request an additional table for the group statistic. Those both just are the output when you run that t-test, as I demonstrated. Then you're showing the error bar chart. So again, this is also just giving a visual of what our data is doing. So using the error bar chart, where the bars represent the standard deviation with the multiplier 2, that's just showing you, again, kind of the spread of the data, where the bars are going to represent the mean talking percentages across that 10-minute duration by group. So it's broken up by group, and setting so that the bars represent standard deviation is just giving you that spread of how spread out is each group individually. So rather than looking at all the data together to get a sense of its overall spread, we're looking at it by group. And then your results summary, which I've already talked about how you add that text note. We've done that before in previous assignments. You're going to report the descriptives, the inferential statistics from the table, both tables I was just breaking down, show you that. Make a comment on the Levine's test, so which were you able to assume equal variances or not, and the result of that Levine's test. And then in plain English, what do the results mean? So was it statistically significant? And whether it was or wasn't, what does this mean in real world terms? So what is the context? And what to submit. You're just going to submit that output file, the SPV file, because that will show everything I need. The output tables, the original output tables that come from your t-test, the error bar chart, and then your write-up. If you have made it this far, I decided to include a bonus question. You can take the same approach that we do for this part 3, where you can just insert a text note or even submit a note on your assignment. Some of you guys leave comments to me after you submit your assignment. That's fine too. But text note in the output file or a comment on the assignment. So based on the results of the statistical test, I want you to leave a comment or a note discussing any methodological problems. So when we go back to just kind of the overview. So again, whether it's significant or not, I just want you to talk about any issues you find with the variables, how we collected them, how we're conceptualizing them. So that could be related to the experimental manipulation, so the stress variable, so low or high stress. If you have other ideas or rationale for why this should maybe be measured, or I should say manipulated differently, since this is our independent variable. You could also bring up any issues that maybe you feel you have with our outcome variable, which is percentage of time talking during the 10-minute interaction. So any comments on method, again, whether it's related to the experimental manipulation or independent variable, so low or high stress, how we manipulated this, if there's a better way to manipulate this, or just even should it be called something else? Like, are we conceptualizing low or high stress incorrectly? Correctly? I don't know. As well as our outcome variable. Are there any issues with this kind of behavioral outcome variable, or even talk like this? Not even that it's behavioral, but that it's talking specifically. So any sort of critiques slash rationale for why something else would be more valid, or it doesn't even have to necessarily be replaced, but you say, well, I would supplement this with this, whatever it may be. So it doesn't have to be get rid of this variable. It could be I would like to supplement it with something else to address X, Y, and Z weakness of this approach. So any sort of, commentary on what's wrong with this method or what's not wrong with it. Why do you think it works? It can go both ways, but some sort of commentary or critique where you're looking at how well these variables are measuring what we're trying to get them to measure, or if they're lacking in some way and could be supplemented with something else, if we should be collecting data on additional variables instead of looking at it like this. Okay, I'll stop there. But essentially, an extra credit question of up to 3 points, depending on your answer. So it's not all or none. Essentially, I'll look at your response and decide how critically you're thinking about it and whether or not you have kind of rationale to support the changes you're suggesting or the lack of changes you're suggesting, why you're saying this is a good method or these are good variables for what we're looking for. So if you made it that far, you have the opportunity to get, 3 extra points on a 20-point assignment. I feel like that's pretty significant, especially since most of you guys do really well on these assignments. So easy points here that you can gain. This assignment is due on November 1st, so this coming Saturday. Again, this is a very straightforward assignment in terms of there's not a lot you have to do in SPSS that I have not directly shown you. Really, the significant part of this assignment is coming from the thought you're putting into after you do this statistical test in SPSS. How are you reading the output, interpreting the results, putting that into words? So that is really the objective, but rather straightforward in terms of what you have to do in SPSS. I've given you the data, I've told you the experimental design, what variables to test, there's only 2, and exactly where to put them in what statistical test and what you expect to get out of that, and then the chart to build after that, which is very straightforward. So reach out if you have any questions. Per usual, I have office hours. This is my obligatory mention that I have office hours Tuesdays and Thursdays from 4 to 5 p.m. Some of you guys let me know when you're coming, which I really appreciate, just so, I know that to expect someone. Sometimes I wait to see if someone's going to join because it feels silly having the Zoom open, but I'm always available at those times. And you can also schedule a different appointment with me, so if those times don't work for you, please don't feel like you're missing out on an opportunity to talk to me. I'm happy to schedule something else with you. But yeah, I hope you guys are excited for this being the last required SPSS assignment. So there will be 2 additional assignments in the coming weeks where you have the opportunity to maybe earn some points back from previous lab assignments or just other areas of the class you need extra points. This is a great opportunity for that. So please reach out if you have any questions. Good luck on the assignment, and I hope you guys have a great week.